Okay, there we go. So anyway, let's take a look at this now. What we're gonna talk about today. I'll just give you a little preface here, so you have an idea what we're gonna be visiting about. We talked about order of operations stuff yesterday, and looking through what you've been doing, it seems to be going pretty well. Is that correct? I mean, looking at the scores and looking on Moodle, it seemed like people were doing pretty well on that stuff. We'll get down there today, and we'll kind of let you guys finish that up, and if there are some questions hanging on, we'll take care of those. But I want to move on to the next topic, which is very much related. We're going to work on solving for a variable in an equation. Okay, and the thing I want you to know about this is that when you solve for a variable, we're going to use the same order of operations stuff we did yesterday. The only difference being, if I write down my order of operations, the stuff we did yesterday was simplify. Okay, that means we were started with a bunch of numbers, and they were all jumbled up with operations, and we wanted to break it down into a single number, right? So when we simplify, we used a normal top-down direction for order of operations. P comes first, then E, then MD, and then AS, right? But today, we're going to look at something a little different. If we want to solve or isolate a variable, and let's just call it X for now, it doesn't have to be X, but if we're going to solve for a variable or isolate a variable, we reverse the order of operations and we go bottom up. Okay, so what that means is the steps that you're going to do to solve for X are already planned out for you. First, you're going to try to add or subtract something to both sides of the equation. Then you're going to multiply or divide both sides of the equation by something. And then we won't even really get to this stuff with a lot of the problems that we're doing now. But later on, really more next year than this year, then we'll deal with, with either doing or undoing exponents on both sides, and then finally with undoing parentheses or grouping stuff. But we won't really deal with a lot. Mostly, we're just going to be dealing with the first two layers when we solve equations. Okay? So let's look at that in action a little bit here. Okay, so what is an equation? Well, I mean, equation, I should probably ask you that first, but an equation just involves an equal sign, right? It's a statement where we have two expressions that are equal to each other, so it has to have an equal sign in it. If it doesn't have an equal sign, that would be like an expression. So an example of an expression would be something like 2x plus 4. By itself, that's just an expression. Okay, but if I add an equal sign to it, something like that, now all of a sudden that whole thing becomes an equation. Okay? Just so we get our terminology straight here. So obviously here, take a look, don't say anything, just take a quick glance. I mean, this is pretty basic. Which of those are equations? What do you think? A and D. What would you call the other two? Expressions. Good. Okay, properties of equality. Now this sounds fancy and high power and very math-like, but we're going to boil this down to a real simple concept. The addition property of equality just says you can add the same term to both sides of an equation. Okay. Oh, and by the way, we'll throughout the year I want to make sure that these math words that you're used to hearing, I want to make sure that they make sense to you. What does it mean when I say term? Let me define that for you. What's that mean? What do you think? It could be, sure. Well, let me have everybody, I want all iPods and all that stuff put away, please. While we're in here, that stuff has to be gone. Could be stuff like that. More generally, a term just means something in math that is added or subtracted. That's what a term means. Okay, so it makes sense in the context of this sentence. The addition property of equality says we can add the same thing. The same math thing is called a term. Okay, things that are added or subtracted to both sides of an equation. Could be a number, could be a variable, could be 5x, could be lots of things. As long as you're adding it or subtracting it in a math situation, we call it a term. Okay, what's the other one? Well, we also have the subtraction property of equality, which just says a very similar type thing. We can subtract the same term. Notice that we get the same word there. The same term from both sides of an equation if we want to. Okay. This, you know what, this PowerPoint's a little bit messed up there. I gotta change something. That shouldn't say term this time. That should say factor. The multiplication property of equality says you can multiply both sides of an equation by the same factor. And what do you suppose factor means in math? Term means stuff that you can add or subtract. Things that can be added or subtracted. What do factors mean? Yeah, multiplied or divided. Right. Stuff that can be multiplied or divided would be called a factor. And I'll change that. Okay, so and then, of course, the division property, as you might expect, same kind of thing. It says we can divide both sides of an equation by the same factor. But what these really mean, instead of remembering all those four properties, all it really means is that in an equation, we have to treat both sides equally. So whatever we do to one side, whatever arithmetic stuff we do, adding, subtracting, multiplying, dividing, we do to one side, got to do it to the other also. Got to treat both sides equally, which of course you already knew. Okay, so now to solve an equation for a variable, this is what I briefly talked to you about just a second ago. We're going to do the order of operations backwards. We're going to undo the normal order of operations. So first we add or subtract, then we multiply or divide, and then later on we'll undo other things too, like exponents and roots and things. But for now, that's all we need. And we keep going until we have isolated the variable on one side of the equation, so it's by itself. That's why whenever we solve stuff, that is synonymous. It means the same thing as saying, oops, isolate. Same thing. Solving and isolating mean the same thing. Get the variable by itself. Okay, we may have to simplify each side first, so we might have to do some things, and we'll look at a couple examples here, like collect like terms, or stuff like that, distribute maybe. Okay, here's an example. Now I want you guys walk me through this. If I want to isolate the x there, solve for x, or isolate the x, what's the first thing I'm going to do? Don't say it yet. Let me write down the order of operations tree first, so we have something to look at. Now, if we're solving or isolating, which direction do we go on the order of operations tree? Bottom up, top down? Bottom up. We're going backwards, right? If we're isolating or solving, we go that way. So now, what's the first step? I saw some hands. Yes, ma'am? Subtract 8. Good. Okay, and we're going to check that one off. Okay, good. Now what? What do you think? Yes, Blaine. Okay, good. We're going to, now this is kind of an important point here. X is being multiplied by 2/9, right? And so technically, if we want to undo multiplication, we would divide both sides by 2/9, but we don't like to divide by fractions. That's clumsy. What do we always do instead of dividing by a fraction? Good. We multiply by the reciprocal. Okay. So it's always equivalent to dividing by a fraction, but it makes things much easier. So if we multiply both sides through by 9/2, that's going to be an easier thing to do. Now what happens? 9/2 times 2/9. Well, look, the 9's cancel and the 2's cancel, and it goes away like we wanted it to. Okay, so then we end up with 8 times 9/2. Now, how do we deal with that? I know this is pretty basic, but we're still kind of in review mode here. How do we deal with multiplying 8 times 9/2? What do you think? Somebody new here. Somebody help me out here. How do we multiply fractions in general? Well, we multiply, 9/2 is the reciprocal. right? But how do I multiply? If I'm multiplying two fractions, what's the rule? I multiply straight across. Remember hearing that? You multiply straight across. Well, 8 doesn't look like a fraction, but is it? Sure, it is, isn't it? How do I write 8 as a fraction? 8 over 1. Okay, now I can just multiply straight across. I have the option here. I could multiply straight across. Now watch these two different ways we could do this. If I multiply straight across, 8 times 9 is 72 over 1 times 2 is 2. And that's equal to what? 72 divided by 2. That's kind of a big number to deal with, isn't it? 36. Okay, can anybody tell me a way I could have done that same process and maybe not had to divide such big numbers? Yes, ma'am? Okay, good. We could have cross-canceled, couldn't we? When we are multiplying fractions, we can simplify before we multiply sometimes, right? So we can see, do we have any common factors in the top and the bottom? Well, it looks like 2 goes into 2 and 8, right? So we could do some cross-canceling there, some cross-reducing. 8 over 2 reduces to 4 over 1, right? Everybody see that? And now when we multiply straight across, we're dealing with smaller numbers. We've got 4 times 9 is 36 over 1. Well, that's just 36. Okay? See how that's easier in a way? Small stuff, but it all kind of contributes. All right. So, there's our answer. Let's try another one. Okay, what about this one? Now take a look, stare at this for a second. Okay, see lots of x's there, right? If we're supposed to isolate x, we got a little bit of a problem. Now, the reversing order of operations, isolating a variable, if I go back a slide here, oh, I can't. Yeah, actually, yeah, I can. Try this. Oh, never mind. The reversing order of operations thing that we talked about, that's only going to work if I can point at a single variable, and that's something you'll hear me say a lot. If you can point to a single variable, you can always reverse order of operations and isolate it. But we can't do that yet. There are a bunch of x's up there. So what do we have to do first? Yes, ma'am? Okay, good. We got to distribute. We got to simplify some stuff and clean it up. So if I distribute the 5 over here, what am I going to get? Okay, negative 10, but also 5x. Okay, because when I distribute, I have to multiply the 5 by both terms, right? So 5x minus 10, and then what about here? Negative 8x, good. So I'm going to distribute the whole negative 4. And then what's negative 4 times positive 7? Negative 28. Okay, good. So there's the first step. We distribute. Okay, that helps. Good. Looking better. Looks a little less messy. It looks simpler, doesn't it? We've simplified a little bit. What else? Before I can point to a single x, what else do I have to do? Combine like terms. Okay, so as it stands right now on the left side, if I just look at the left side of the equation, can I combine like terms? No, those are unlike, aren't they? What about the right side? Yeah. Okay, what do I get? Negative 7x minus 28, sure, okay. And then, now here's a seemingly minor point, but I want to make it anyway. Which side should I probably put the x's on, and why? What do you think? Anybody got it? Oh, hang tight. Let's see if anybody else. Anybody? Oh, the bigger number side. Good. That's what you're saying, right? So which number is bigger? Okay, but we're dealing with we want to isolate the variable, the x. So which side am I going to push the x's to? Good, because 5 is greater than negative 7, right? So we always want to push the numbers to the side where I'm going to have the biggest number, push the variables to the side where there's going to be the biggest number of them, the positive number of them. How come? Yeah, because I don't want to eventually have to divide by negative. It's not a huge deal, but we'd rather make things as simple as possible. So as a rule, we're always going to push stuff in the direction of the bigger number of x's. How do I push something to the right there? How do I get that negative 7x off of the right side onto the left? Add it. Good. So I'm going to add 7x to both sides. Now, at last, after all that work, look what I've accomplished. I've now got a single x that I can point at, and so I can always isolate it. Now that I finally have simplified this whole thing, if I just go backwards through order of operations, I'll isolate that x. So now what are the two steps in order that I'm going to have to do to get that x by itself? First, I add 10, good. And then divide by 12, sure. And then what does that simplify to? What's the biggest number that divides into both 12 and 18? 6 does, doesn't it? So how many times does 6 go into 18? 3 goes into 12. So it's negative 3/2 then, right? Okay, good, good. Okay, does that make sense?
Yeah.
Okay, and I know, I'm probably talking, I'm going slow through this, but I think it's important at the start of the year. A lot of people know how to do this stuff and instinctually and sort of, they have a feel for it. But a lot of times people don't understand always what they're doing. And it's critically important as you start to move forward into big time math classes, harder and harder math classes. If you can be really systematic about this and you can get this down so you understand what this process is, this is the same process you're going to use on a really hard problem in pre-calculus or algebra 2 or something. Okay? All right, last one I want to look at. Actually, 2 more, I think. Okay, what about one like this? Now this, let's talk about this. Any suggestions? There's more than one way to do this problem, by the way. We're just going to look for the easiest way. What do I technically, if I want to get those x's by them, I have 2 x's, what would I have to do there? What did we do last time when we had multiple x's? Combine like terms. Now what's the problem with combining like terms here? Well, yeah, I've got a 2/3 x and a 2x. If I combine like terms, I'm having to add up a bunch of fractions, right? And it gets worse. Even if I did, let's say I push all the x's over here because 2 is bigger than 2/3, and I'm going to get some fractional number of x's, right? Then when I push the other numbers the other way, I'm going to have 1/5 plus 3/10. I got to deal with fractions again. I'm going to be fighting fractions the whole time, right? Wouldn't it be great if we could just get rid of the fractions to begin with and then do the problem without fractions? Wouldn't that be awesome? Is there a way to do that? How do we do it? Yes, sir?
You change them to decimals.
You could, but what if it's a repeating decimal? What if like 2/3 doesn't become a decimal? It repeats forever. It doesn't terminate, so that makes it tough. It's an idea. It's not a bad idea, but maybe there's something we can do that's even easier. Have you ever heard of clearing the fractions before? Haven't heard that? Oh, this is a great trick. This is an awesome trick. Now remember this one. This is big. You'll get a chance to do it on the assignment a little bit. Here's how you clear fractions. It's very simple. All you do is you look at all the denominators in the entire equation. So what are the denominators for me? 10, 5, 3, right? The bottoms of the fractions. 10, 5, and 3. I want to find, ideally, it doesn't have to be, but it makes it easier if I can find the smallest common multiple of those numbers, meaning the smallest number that they would all divide into. Okay, so I've got the numbers 3, 5, and 10. What's the smallest number that I could find that they would all divide into? 30. Okay, how do we get that? Well, if you look at the product of the smaller two, I get 15, and 10 doesn't go into that, does it? Right? So then I've got to find a number that 15 and 10 both go into, and I have to just, that'd be 30, wouldn't it? Right? Okay, so 30 is my number. Now, what do I do with that? With the number 30, I'm just going to multiply that through. Well, that doesn't show up real well, does it? I'm going to multiply that 30 through by both sides. Okay? Now watch what happens when I do that. I want to do this, and it's going to seem like I'm really making this longer than it needs to be, but there's a reason for this. If we can do this correctly once, you'll have this down. How am I going to do that? If I want to distribute the 30 through to all those fractions, what do I get? What about the first distribution? If I take 30 times 2/3, well, let's just look at that. 30 over 1 times 2 over 3 is what? $60 over 3, which is what? 20? Okay. Now, could we have done some cross-canceling there?
Yeah.
We could, couldn't we? We could have made that a 10 and that a 1, couldn't we? Because 30 over 3 reduces to 10 over 1. And then that would get us to 20 a little easier, right? So the first distribution is going to give me 20x. Yes, ma'am? Oh, nope. Okay. That was a question. And then what if I distribute 30 to 1/5? Same kind of deal, right? I've got 30 over 1 times 1 over 5. Well, that's just 30 over 5, right? What is that? 6, okay. So plus 6. Now we got to go on this side. That's an easier one. I don't have to do any canceling here. I'm just multiplying. What's 30 times 2x? 60x. And then finally, 30 times negative 3/10. Well, 30 times 3/10. What can I reduce there? Okay, so that becomes 3 over 1. If I multiply straight across, I get 9 over 1, which is 9. And I got a minus sign. Make sense? Okay, now that's much, much easier now, right? That's no big deal. We can take it from there. But before we do that, I want to show you a trick for getting all these numbers. Okay, we wrote them out separately, but watch this. This really makes this short. Okay, when I'm distributing my 30, think how we built that 30. We built that 30 from the numbers 3, 5, and 10. It's a specially chosen number that we know 3 and 5 and 10 all divide into. For sure, they have to, right? That's the way we built it. We found, remember what we did? We found the smallest common multiple of all three of those. Smallest number we could build by multiplying those together, all three of them together, right? Or that they all divide into, I should say. So we already know that these numbers fit perfectly with 30. So when we distribute the 30, we can be guaranteed every time that we're going to be able to reduce before we multiply. We have to. That's why we picked 30. So now watch what happens when we distribute that 30 into the 2/3. Here's what you do. You just say 30 divided by 3 is what? 10. And 10's the number that gets multiplied by the top. Isn't that easier? Every time you can do that. Whenever you're clearing fractions like this, that technique will always work. So 10 times 2, those cancel. That becomes a 10, and that gives us our 20x. Same thing here. 30 over 5 is what? 6 times 1 is 6. Isn't that easy? Other side, 30 times 2x, well, that's just our 60x. We don't need it there. But here's another fraction. 30 over 10 is 3 times 3. How about that? Simple, right? Okay? You'll get a chance to try this, too. I'm going to get you down there so you can. Okay, so what do we get after that? So we get it to there. Now it's a piece of cake. I still have two x's though. Until I can point to a single x, I can't reverse the order of operations and isolate. So what do I have to do first? Subtract 20x from both sides. Now I think they did this backwards. Did they? Yeah, we're not going to do it that way. We'll take it from there. We won't bother with them. So if we subtract 20x from both sides, we're going to get a, whoops, we're going to get a, oh, geez. We're going to get, a 6. No, we're not. Now we are. There we go. We're going to get a 6. And then on this side, 60x minus 20x, 40x. What's next? Add 9 to both sides. Okay, if I add 9 to both sides, I'm going to get what on the left? 15, okay. And then I've got a 40x. And then last step? Divide by 40. Good. Does that make sense? We got to divide by 40 then? Everyone sees that we got to add 9 to both sides, but if I want to get the x by itself, how do I undo multiplying by 40? Divide by 40. So that cancels, and we get x equals 15/40, which reduces. Yeah, what's the biggest number that divides into both 15 and 40? 5 does, good. So 5 goes into 15 3 times, into 40 8 times, and there's our answer. Okay? Make sense? Good. Okay, last thing I want to show you. Okay, good. Now look what they did. Because this isn't horrible, but because they subtracted 60x to this side, they got negative numbers in here. It's not that bad, but it's easier to deal with positives. Okay, what about this one? What do I do here? Got to distribute, good. I have to simplify. I have 2 x's there that I can point out. I need 1, so I got to simplify. If I distribute, I get 5x minus 20 equals 5x plus 12. Now, hold it. What's going on here? What do I do next? Yeah, if I subtract 5x from both sides, look what happens. I get a weird statement, an untrue statement. Negative 20 equals 12. Now, how often does that happen? Never, right? So then, how many values of x are going to work up here? How many values of x are going to actually make that equation true to begin with? And then when we're solving, we're just finding the values of x that work. Are there any? No. Whenever we get a statement like this that says that doesn't make any sense, you know, that's an untrue always, the way we interpret that is there's no solution. There is no value of x that works. Nothing we could ever choose would make that equation true. Okay? Now, similar to that, what about this guy? What would I do here? What do you think? Can I do some on the left side? Combine like terms. 7x minus 3x gives us 4x plus 14 equals 4x plus 14. So if I subtract 4x from both sides, and I subtract 14 from both sides, I get another kind of weird statement. I get the statement 0 equals 0. Now, how often is that true? Always. So how do you suppose we interpret that? This meant there were no solutions, no values of x. The other problems that we've worked with today, prior to this screen, we got examples where we had one answer for x. What does this mean? Infinite. Yeah, good. This means that all real numbers work. Or on the assignment that you're going to do, you're going to choose, I think, infinitely many. Same thing. All values of x would work. Okay? Does that make sense? Okay? Let's go work on it.